Well, thank you so much for those kind words of introduction. Appreciate that. Let me also thank the organizers of this conference, in particular Dr. Hvac for inviting me to be here at this keynote session. And I know it's the last session, keynote session, the last day of the conference. And after that wonderful evening we had yesterday, the museum visit and the dinner, it's good to see so many of you back here at the start time. My topic is, as you see on the slide, sustainable HVAC technologies for occupant comfort and well-being in the built environment. And I was listening to Professor Tim Nguyen's keynote yesterday, and at the end of it felt that what I'm going to be sharing with you this morning is a nice add-on to some of the points that he had raised in his keynote talk. I will start off by first turning on this gadget I have in front of me, a technology. So I'll start off by just giving you an outline of what I'm going to be addressing this morning, with some background of what the topic is about, and I would address the energy issues that has been mentioned by pretty much all the previous keynote speakers in the last couple of days. I'll also talk a little bit about the indoor air quality issues and how and why that's important to be seen in the overall context of what we need to have in the built environment. And I'll focus a good part of my talk on the sustainable HVAC technologies. And I will again highlight the areas in which I'm going to be focusing that part of my talk, and finally have some concluding remarks. This is a good place for me to start by saying where the focus ought to be in the context of the built environment. I have, for a good number of years now, in my lectures to my students, as well as to my PhD students as well, taken this approach where we said, okay, let's look at, it's not just energy all the time. It's important. Energy efficiency has to be at the forefront of what we do. But I think we should not forget what the built environment, what the buildings are for, whom are they catering to, especially when it comes to comfort and places where people are going to be occupying. So this whole notion of healthy becomes a key word. So energy efficient, healthy buildings, if we look at that context, of course, comfort, thermal comfort, indoor air quality, energy, greenhouse gas reduction, these are all some of the important points that we need to keep in mind. And you can begin to see that an integrated approach is almost absolutely essential to ensure that this thing gets delivered. And of course, it's not just what happens down here in the operation stage of a building or a facility. It's got to start from day one, from the design process. And here you're looking at a process where the entire process of designing the building, installation as part of the construction and project management process, commissioning, and finally into the facilities management part. So it's absolutely crucial that we focus on what happens right from the outset in order to be able to deliver that kind of quality built environment we are talking about. Let me just start off by putting some context to what I want to talk about in terms of why this energy issue is so important and why the future designs need to be looking at it in a very holistic manner. I think the point has been very well made right from the first keynote speaker to yesterday's keynote presentations, where the growth in terms of the energy demand, this is slightly dated, but then the coverage for this slide goes up to 2030. The important point to take note of here is in the context of total energy delivered, the demand for it, I mean. If you look at the non-OECD countries, there they are. The growth rate is phenomenal. I think you don't have to say anything more on this point. The demand is phenomenal. And if you look at what is happening in the commercial sector in terms of the buildings, office buildings, schools, stores, and the various types of built environment, Again, you can see that the demand in the non-OECD countries, as Professor Tim Vance very rightly pointed out yesterday, is really phenomenal. Now, if we are focusing on energy efficient, healthy buildings, I split the requirements in terms of what we need for occupant comfort and well-being into two primary considerations, thermal and IAQ. I say thermal because that's the first thing that we talk about in terms of how we're going to maintain the temperature condition. I mean, that's the first thing that comes to our mind. Is the place warm? Is the place cool? Depending on where you are in the world. So one of the things that we advocate for the thermal aspect is let's try to optimize the passive design. This is almost like how I would tell my students in the curriculum. Say, you got to focus on the passive design, but that's where the energy efficiency equation starts to begin. Even before you started talking about any active systems, we had to ensure that it's optimized in its passive design features in the best possible manner. And then we go on to active systems, be it lighting. Have we taken enough daylight into the building? Be it air conditioning. Have we reduced the demand for air conditioning? These are some of the questions that one would start asking right from day one, from the beginning. And then it comes to the indoor environmental quality that relates more to the thermal comfort and the occupant well-being and the air quality aspects of it. We have two important things, very similar to the approach that's taken here. Can we look at source control? Can we then go on to exposure control? I will highlight a few of these points as we go along. I start off with this simple concept or schematic concept of what happens in air conditioning design, air conditioning systems in, say, medium to large buildings. And the concept is very much similar to even a single family dwelling or residential context. We got the air conditioning system starting from, let's say I'm coming from inside out, so to speak, from the rooms for the built environment to the external. We have the air handling unit, then we have the chill water system. In our case, I'm talking about cooling application, cooling and drying applications. And then we have the, finally, the refrigeration cycle is over here, and finally the heat rejection cycle. So if I look at this schematic concept for any building, small, medium, large facility, mega projects or whatever, the concept is exactly the same. And then we start looking at where are the energy implications, where are the big energy guzzlers, chillers. The size of the bubble gives an indication of the extent to which this energy is involved. Then the air handling units, the fans, consume quite a bit of energy in the process of achieving that comfort that we're talking about for the occupants in the building. And then we have all the other auxiliary sort of equipment, the cooling tower fan, the pumps, condenser water pumps, the chill water pumps, all of them add to the primary energy consumption in the buildings. So I am going to be focusing, just to get the context right, I'm not going to talk too much about the chiller side of discussion here, because one of the things, I'm again speaking from our own experience in Singapore, I will mention a little bit about how the kind of requirements from, say, rating systems or regulatory requirements went to a very large extent to focus on chiller performance. And today, I believe some of the requirements that we have, which I'll highlight later in this presentation, that we have for building design from an air conditioning point of view is quite I would say, reasonably, I would say, challenging. So the chiller performance in terms of the primary energy consumption, this big bubble, we believe is being addressed reasonably well. What has not been happening much is over here in terms of the air handling here. Not so much in terms of whether we are picking the right fan and how, what kind of capacity of fan we have, but I think it's the context of how do we manage this entire business here? How do we distribute air? How do we provide ventilation? How do we take care of various demands in the building? How do we provide for flexibility? So my presentation later in terms of technology is going to be focused more so on the air distribution side, the air conditioning, what's happening in the air handling unit, and what we could do better in terms of air distribution. That's where I'm going to be focusing my technologies-related input a bit later. So I also use this information that several speakers had used in the last couple of days. What struck me as an interesting observation here was if you look at the various loads over here, the energy intensity delivered, and if you look at what's happening in terms of heating, cooling, and ventilation compared to, say, between 2013 and 2040, the prediction is that the energy demand for HVAC is likely to reduce. Now, that's very, very interesting. I think it's also very promising for us as a community to say that we are doing quite a fair amount of work and effort in trying to reduce that energy consumption. And that's true because we are trying to address what I just said in terms of chiller energy efficiency performance, in terms of the overall air handling unit design and how it's distributed, how the air is distributed. So there's a lot that's happening in terms of how you would address the HVAC energy performance. I thought that was very interesting, and as we move forward in terms of addressing comfort, ventilation, indoor air quality issues, the air conditioning related energy consumption, now if you look at the whole context of chiller and AHU and all this stuff, together they constitute a fair amount of energy. I mean, in the tropics, it's easily about 50 to 60% of the total energy consumption in buildings goes towards air conditioning. And if we can reduce the demand and reduce the proportion, that's going to be a pretty impressive effort towards going for low energy buildings and zero energy buildings. So now let me just try to change the gear towards indoor environmental quality. And I think the focus here has historically been on thermal comfort and indoor air quality. I think it's not because it's less important to address the lighting and the acoustics issues, which are equally important in indoor environmental quality. In fact, in ASHRAE, we have a guideline project committee that addresses this integration or interactions amongst these various human requirements. It's called GPC 10. And they publish a document. There's a current one. I think it's dated 2013. If you have had a chance to look at it, you'll notice that what's discussed there is the interactions amongst thermal indoor air quality lighting. In other words, if you try to optimize the thermal comfort performance, does it adversely affect your indoor air quality, and does it affect your lighting, and is there an implication on acoustics and that kind of thing? I think it's important to address this in an integrated manner, which again, in yesterday's presentation, Professor Tim Vance very rightly highlighted the integrated building performance, extremely important aspect. Having said that, I'm going to focus on the thermal comfort and indoor air quality aspect. Because when it comes to the air conditioning systems, the HVAC systems, these two are the more directly affected performance mandates compared to, say, the lighting and the acoustics aspects. Now, why am I bringing this particular comfort zone chart, thermal comfort zone chart from ASHRAE Standard 55, 2013? Just to highlight an important point that was also discussed yesterday at some stage, what do we design for in terms of thermal conditions, thermal comfort? What's comfortable today? Is it going to change in the future? And I think ASHRAE acknowledges this and has acknowledged this always, and we have these kind of these colored boxes that just popped onto the chart, basically says that, okay, here you would probably want to do something like this. Perhaps for your, or this something like the blue for your winter places. Keep cooler, you save energy, can you get comfort here? And there's a range, a winter comfort zone. And there's a summer thermal comfort zone, the green. So if I'm talking about hot and dry, hot and humid climates, would I want to be in the red zone or would I want to be in the green zone from an energy point of view? Both would be comfortable. It depends on how we design it. It depends on how we manage it, how do we operate it. So if we were to be on the warmer side of the comfort zone and still be able to achieve thermal comfort, because it's not just temperature alone that gives comfort, there are other factors that impact comfort. And more importantly, or in fact, the more pertinent point here is, can we use air movement to get our thermal comfort in situations where the temperatures are slightly warmer? And what are the important I would say recommendations that's come in the recent versions of ASHRAE Standard 55 is to talk in terms of elevated airspeed at elevated temperatures, which will then allow us to be comfortable. So it does not always have to be just cool temperatures that give comfort. It can be a combination of temperature and airspeed, and that's what it allows. In the standard, we have pretty good guidance in terms of how that can be achieved. Moving forward on the indoor air quality aspect. Here is a study. There's tons of such studies reported in the scientific literature. This is by a group of very eminent scientists and professors working in this field from Berkeley, Finland, and elsewhere. I know quite a few of them there in the authorship. What they reported here is very apt and appropriate for us to be reminded that providing the right quality of indoor environment has an economic benefit. It's absolutely clear. So many studies, even more recent ones that's been published, which talks about this point. In fact, it's very clearly stated here that if you improve the building environments, it could have health benefits for more than 15 million to 89 million of US indoor workers with that kind of economic benefits. And this was published back in 2002. So if we accept this sort of an impact with good indoor environmental quality, there's no reason to not consider that seriously and not address that from every individual point of view. I mean, we set 80-20 rule for comfort and other standards. It doesn't have to be that. Can we create systems and technology implementation in such a way that every occupant in a building can demand and can get his own built environment? I mean, the technology is heading towards that. There are ways by which this can be integrated, interface with the way the system is going to be working, and that's exactly, I think, where we are headed towards in the future. I was talking to Professor Tim Vance last night and said, look, this is my favorite quotation as well. Since he spoke about this yesterday, I thought I'll have a little quiz here. What did the scientist Pettenkofer say? Anyone? Those of you who are here, just a refresher, he said this. He said, don't try to use dilution. So the famous kind of saying, the solution to pollution is dilution, is not the way to go. That's not going to get us our energy efficiency. It's not going to get us the right quality of indoor environment. If there is a source, let's get rid of it. Source control is what Pettenkofer advocated, and I think there's a lot of merit in this philosophy. And this philosophy is carried in a lot of standard development, standardization activities. In fact, if you look at the European standards for ventilation and indoor air quality, they have very clearly implemented this kind of a thinking in their requirements, ventilation requirements. They have, in ASHRAE standard, we have just one column, right? For people component, ventilation rate, and for area emission component, for pollution emission. In the European standards, in SEN and other European standards, there are two columns. One is for non-low polluting materials. In other words, the standard one, the one that keep polluting. And then there's another column for low polluting materials. When you choose as an architect, as a designer for interior environments, if you choose materials that are low polluting, you can actually design for lower ventilation rate, and that means you actually save energy because you don't have to take that much more ventilation there. So this is a great philosophy to consider, source control. Having done the source control the most efficient manner that we can think about, in the most optimal manner we can think about, then obviously we have to go for ventilation, exposure control, and that's important. Without the exposure control, we can't ensure that quality of built environment that we can actually create for the occupants in the buildings. So what's exactly ventilation doing in so many of these points that are highlighted here? Well, dilution is the most fundamental thing. Minimize occupant exposure from a health implication point of view. I will talk a little bit more about this as we go along. Airborne infection control, something that we can very clearly think about. In fact, ASHRAE has a position document on airborne infection control. I was part of it about 3-5 years ago. And we identified that ventilation, meaning outdoor air being brought to the occupied breathing zone, done correctly, can be a way to help mitigate the spread of airborne infection. I will again talk a little bit more about how this can be done towards the later part of my talk this morning. And then, of course, we have naturally ventilated or mechanically ventilated environments. There are issues in both. And one of the things that I've been talking to some of the participants here in the last couple of days, when you have an external environment that is very polluted and you have naturally ventilated designs for residential dwellings and apartments, it becomes a big challenge. How do you ensure ventilation in those cases? So we do need to think in terms of filtering those pollutants off the outdoor air before we can use that for ventilation. And of course, Hvac is the most important part of it, related to mechanical ventilation and the energy implication. They're all important points related to exposure control or ventilation in the context of indoor air quality. I'm presenting this particular slide. I can talk a lot about this slide, which includes some of the work that we did over here, the tropical climate ventilation measurements. What it does is it's a snapshot comparison of all the reported information about ventilation, air change rate measurements done in Europe, Nordic climate, continental Europe, Mediterranean Europe, oceanic Europe, and then our own air change rate measurements. We've been doing this work for quite some time in our group, and this is work being done in the late 90s, early 2000s sort of a time frame. What we find is in our buildings, because of the energy implication, there's a fairly high amount of recirculation that is used. And because of recirculation, when you compute the outdoor air change rate, it's quite small, quite low. And this is the requirement for the entire year. Whereas if you look at this huge spread that you see in the continental Europe and other climatic conditions in the temperate climate zones, there are times of the year when the outside air is so perfect, you don't need to cool, you don't need to heat, you just need to take it from outdoor and put it indoor. And that acts as of course you could filter it if you need it, and that's why you have very high air change rate in some of these measurements reported, studies reported. So it's not to say that we are under-ventilating the space here, because this ventilation, one outside air change rate throughout the year is to ensure that compliance to local ventilation codes, even ASHRAE 62.1, if that's what the basis is done in all our buildings. If the ventilation rate is very low, I mean, this, I can tell you as a fact from observation, from measurements, this typically turns out to be about 1 to 1.2 air change per hour. If you do measurements using tracer gas and other means, that's what we would get. So typically, systems are designed to provide that sort of an air change, and that's what we get. And I always found this comparison very useful to highlight the fact that there are certain places where you can actually flush more outside air in different times compared to what can be done in certain climatic zones. Again, from an indoor air quality, educational point of view and design guidance point of view, ASHRAE has this document. It's called the Indoor Air Quality Guide. I would strongly urge you to consider having this as a good reference for indoor air quality. And interestingly enough, I've got this URL. You can look for it on the ASHRAE website. It's freely downloadable, right? It's a very good reference. And it really summarizes a lot of work that's been happening in this area in indoor air quality for the last, I would say, at least about 2 decades or so. Now, if you look at the issues related to indoor air quality and energy, what exactly are they? So we are talking about related issues here. Tight envelopes, very important consideration, especially when you're going to be using air conditioning. Ventilation or the lack of it. I put it as the lack of it to say that if we don't take enough outside air for ventilation purpose, and this could be the case in certain situations when the outside air is very polluted, maybe the regional occurrence, maybe some kind of a periodic occurrence as well, and then the tendency could be, well, let me just cut down the ventilation rate. That's not a good strategy, because you are actually not helping the exposure control of the whole discussion here. So we can't really take the ventilation outside, completely take it out of the whole process. We need to provide for it. So filtration is important, very important consideration over here. Building pressurization and infiltration related to the tight envelopes. So in most countries, I think there's a greater emphasis being laid on how tight the building envelopes are made. And of course, this is a function of several factors. You can't always have good control, complete control on the workmanship and so on. But let's say that we are able to achieve that to a large extent, and you can keep the infiltration out. Because infiltration in a lot of climates is not a good thing to happen. It adversely affects the overall process of energy as well as indoor air quality. Oversized HVAC systems, I will talk a little bit about it in my technologies overview in a short while. And of course, poor system control. I think I called it poor system control. Professor Tim Vance put it very nicely yesterday. We have the capability and the ability to use smart sensing technologies to be able to have better control. And I think he's absolutely right when he says that. Technology is advancing so fast that what was not possible, say, about 5-10 years ago in terms of sensing the contaminant concentrations of different types of pollutants is now becoming that much more feasible. Not just in one central location in an air handling unit, but you can do it exactly where the person is seated, right down where the person is seated in the occupied breathing zone. So you are now able to do such very refined measurements, sensing, that information can be used to control better in terms of the overall system operation. Let me just, as a kind of lead on to the technologies part, say a little bit about some of the rating systems that are prevalent worldwide, and I'm sure most of you in the audience would know several of these rating systems. LEED is, of course, very well known. There's the Australian Green Star rating system, Japanese CASB, UK BREEAM, and there's a whole bunch of rating systems from Canada. I kept the BCA Green Mark to the last because that's from Singapore. BCA stands for our Building and Construction Authority, BCA, and the Green Mark rating system is something that has been developed in Singapore for quite, I would say, not a very long time. It's only about 10, 11 years to be precise. And here is the snapshot of what happened. The first Green Mark rated building was in 2005. It was our National Library Board headquarters building. It's quite a interesting building, designed to bioclimatic requirements of where it is located. A lot of things were taken into consideration. And as of, say, late 2014, we are about 2155 number of buildings that happened in that particular year. So to put all of this in a context, there's a target in Singapore to have by 2030, 80% of all buildings to be Green Mark certified. Now, I had to highlight a couple of things here. It's not just new buildings, it's existing buildings as well. So in our rating system, just like in LEED and others, we have Green Mark for new buildings and Green Mark for existing buildings. And these rating systems don't stay static, they evolve continuously. So the longer or the later one goes through the process of getting the Green Mark rating for an existing building, the more challenging it's going to get. And I've been seeing that for the last 10 years since its evolution. The bar is constantly raised. And it's a good thing as a profession or as a professional setup in Singapore. There is a need and there is an emphasis for all players, all stakeholders involved to be able to get to that stage of performance. And I want to just touch a little bit about this third green building master plan that we are currently going through. Over here, the 3 strategic goals: continued leadership, wider collaboration and engagement, and proven sustainability performance. There's an important part over here I wanted to highlight. That's why I used this particular slide too. We have last September, in the International Green Building Conference, which is held annually in Singapore, launched this Green Mark 2015. Well, the current version is called 4.1, and this will likely be called 5 when it actually gets implemented sometime this year. Last September, it went into a pilot phase. The reason is this version has got some major changes. Major changes. I want to highlight a couple of them which are very interesting and relevant to what we are talking about here. It is actually structured into 4 main parts here. The 5th one is any advanced efforts, green efforts. But the first one is a climate responsive design. I think that's where the passive design part I mentioned earlier comes forward to be considered. We need to optimize on how the building's passive elements will drive towards energy performance. Then we had the building energy performance, resource stewardship, and smart and healthy buildings. I want to just say a little bit about these two aspects. Up until the 4.1, the one that's currently required as a requirement in Singapore, the focus on energy is almost 50%. The weightage is almost 50%. Now, in this version, energy and smart and healthy buildings are going to get equal weightage. So what it means is, of all these four parts that I just mentioned, they have equal weightage in terms of the importance. You can't get points, more points for energy, because that's going to help you in the rating system, because unless you do the smart and healthy building aspect, which is the IEQ aspect, it's going to be extremely challenging. So the main thrust that the BCA Green Marks scheme rating system has done with this new version is lay a stronger emphasis on the IEQ aspect. And this is a step forward, in my opinion. It addresses this whole issue of sustainable design for occupant well-being, or the built environment for the occupants, and to take care of their needs being a more important consideration in the whole process. So the second half of my talk this morning, I'll focus on the sustainable HVAC technologies. And in that context, again, occupant comfort and the well-being part. I mean, here we can talk about this as thermal comfort, and the well-being addresses the indoor air quality and the health-related conditions that can be improved. And what are they? What kind of technologies and what kind of, I suppose, the design concept that one could be looking at here that can help us in this quest forward? In no particular order in terms of its importance, I'll just go through some of these technologies, some of which we have been working as part of my own group's effort, and some that I will highlight here as important and useful in making this discussion meaningful and effective for us as a professional community. Adaptable coils. Now, before I even start talking about what adaptable coils, I would like to highlight this important point about flexibility, or about this capability to adapt system operation in its actual operating condition, irrespective of how it was designed and how it was installed and commissioned. And I think it's important to recognize this, because as we move forward with more smart sensing technologies in place, if we sense certain parameters, and if that particular aggregate of all these parameters calls for a certain action, and if at the infrastructure level we do not have those systems or components or equipment in place, then it's only that good, meaning we cannot achieve the action that we are calling for. So this is one part of what I would like to highlight: flexibility in system operation, modularity in system operation, adaptability in system operation is key to some of the things that we can actually achieve in providing that ideal or optimal built environment for the people. So adaptable coils, what are we talking about? Back in June 2014, ASHRAE had a seminar in one of, this is summer meeting, annual meeting. This was organized by the Thermal Comfort, well, the TC, Thermal Comfort and Human Physiology, TC 2.1, and they called this session, well, in ASHRAE we have some nice catchy titles, right? So we had this, my building is so cold in summer and so hot in winter, what's going on? And I think the thing that we were trying to address here is if we are doing our designs properly, as how it should be, if we have if we have done our designs to be able to adapt to summer or winter condition wherever we are, then why is it that we are not able to provide that comfort? Why are people complaining? Why are people still complaining? Irrespective or notwithstanding the 80-20 rule. We say 80% of the occupants will be satisfied, the other 20%, we allow them to complain, let's say, okay? Which we should not. Everybody should be comfortable. Everybody must be able to provide that comfortable environment for themselves. So this seminar it roughly had those kind of objectives and discussion points. And I was talking on the subject of overcooling in summer. I didn't address the overheating in winter because I don't have too much more experience, but I can share with you anecdotal experience of my own. When we attend some of the ASHRAE winter meetings, it could be freezing outside, snow and ice, and it's really very, very cold. But when you enter into some of the meeting rooms, I sweat. It's really very warm. Well, we could argue that it's probably the control, probably, may well be. Or it may also be the case that when it comes to the comfort zone utilization of where we should be on the comfort range, we use temperature as the more important or the primary consideration of achieving it. So there is a range. In winter, do we design and operate for warmer conditions? And in summer, do we design and operate for cooler conditions? That's the question. So let's see what happens here in terms of the important requirement for cooling application. I'm now going to share with you something about a cooling application, the adaptable coil. The context of a cooling application, the cooling coil and how it performs, it's a function of what the room cooling loads are, typically categorized as room sensible heat ratio, and then the coil sensible heat ratio or sensible heat factor. So the coil performance must be compatible with the room loads or the space cooling loads. Now for design condition, at design stage, we have a certain finite condition that we can do. We said that's what it must be. What happens in reality? No building stays one same load all the time. Loads fluctuate. People walk in and out. Well, look at this room. We are probably about 50% occupied here, maybe slightly less. If the load doubles, then that's what the design load is for this room. So we need to be able to say that systems can adapt itself, the AHU and the cooling coil performance need to adapt itself to what the loads actually exist in the room. These are the fundamental design criteria. But the way we design and make the systems operate, the only thing that we really can do in the air handling unit kind of location is to modulate the chill water flow. And when you throttle the chill water flow to the cooling coil, we do something, again, I'm talking hot, humid climate, we do something that is totally opposite to what we want to happen at that stage. We try to create the surface temperature of that cooling coil now as a heat exchanger for heat and mass transfer. It gets warmer and warmer. When the surface is warmer, you're going to inhibit dehumidification, not enhance dehumidification. Basically, I just said the coil is too big. It's just too big. If we had the ability to take that big coil and put a smaller coil, it would be wonderful. We would have achieved what we want. So can we make that kind of adaptability really happen in the actual design and operation of the coils? So here is one strategy that we have through simulations tried, and it would work from the point of view of making sure the surface temperature is kept cold. At design, if let's say we have a 6-row deep coil, the chill water supply to the row 6, coming out of row 4, we collect it in a manifold, then there is a pathway whereby it goes back to row 3 and out of row 1, and here is a modulating valve. So this is what you would see as a design and operation at the design load. If the loads drop, and then we have a situation where this throttling valve, this modulating valve is throttled and closed, almost closed position, resulting in the surface temperature of this coil getting warmer and warmer, we could do something like that. We could effectively knock out a couple of rows, 3 rows in this case as part of the simulation that we did, where you can knock out and then you have a smaller coil. With a smaller coil, you can now allow the chill water to come back to what the design flow rate should be. So you're actually able to achieve a cooler surface temperature which enhances the cooling and dehumidification, especially the dehumidification part of what we are looking at. And that's what we refer to as adaptable coils in dynamic operation. So this is designed and manufactured and installed as such, and we can make it to work the way we want to in the actual operation. Now we also can combine this with this concept called the low phase velocity and high coolant velocity of the cooling coil operation. The combination of these two, low air side heat transfer coefficient, high water side heat transfer coefficient, actually provides the coldest interface temperature possible. The key objective here being to have that coil always at that kind of a cold interface temperature that will enhance dehumidification to its fullest potential. Let me now go on to this other concept and technology which has been around for some time now, and I think it's got tremendous merit, the dedicated outdoor air system concept, where we are talking about separating the ventilation air, the conditioned outdoor air, from the cooling air or thermal part of the whole process. And then once you're able to do this, and you can if you can distribute it as such to the occupied zones, then you have tremendous potential in terms of what happens in terms of demand ventilation in the occupied zone. So that's a very good thing to happen and take care of. So what exactly is that? We can think in terms of a chilled ceiling. We have the conditioned outdoor air supplied as ventilation air to the space, takes care of the ventilation and indoor air quality, and then the chilled ceiling or radiant cooling panels takes care of your additional cooling requirements. So this is a very interesting, good concept of dedicated outdoor air system. Of course, in certain climatic conditions, we've got to be mindful of the issues of condensation that can happen through infiltration or otherwise, especially in hot and humid climate. But if done correctly, it certainly has tremendous benefits and advantages. We developed something that we've been working on in our group, and that's called the single coil twin fan air conditioning and air distribution system. The idea really is it's a DOAS concept where we separate the ventilation from the cooling. So I just take the schematic of a high-rise building, floor-by-floor air handling units, and this is basically supplying air through the supply diffusers to the space, something well-known concept that we would be very familiar with. So now what we're doing is we have a central rooftop air handling unit, not an air handling unit with a cooling coil, just a fan to push the air down a vertical shaft, of which we can draw the ventilation or outdoor air requirement for each air handling unit, the secondary air handling unit. And the interesting thing that I would like to highlight, there is no cooling or dehumidification. There is just a fan pushing the air down. For that matter, we could have drawn this outside air at each facade if there was indeed such a design possibility there. The difference is this air handling unit is not like a conventional unit. It's got slightly different concept. We actually call it a compartmented air handling unit. The cooling coil is compartmented in two different sections, single chill water flow, but two different sections, and we distribute the air streams separately. So you actually, the green line is ventilation, conditioned outdoor air, the red line is recirculated air for cooling. In the zone, in each zone, you now have the ability of independently controlling ventilation and cooling. So it's demand ventilation, demand cooling at the occupied zone, at each occupied zone. So this is exactly how the AHU looks like. You got one cooling coil, kind of a barrier that separates the two sections, two fans, one for the outside air, another one for the recirculated air, and the two air streams don't mix, they stay separate and distributed as such to the occupied zone. What we are trying to do here is do the outside air treatment separately through part of the cooling coil, and then the recirculated air part which will primarily take care of the sensible cooling or sensible load requirements. And doing a comparison between a conventional system performance to what this can achieve, simply because you can reduce the ventilation based on occupancy demand in the occupied zones, we could see a 10 to 15% energy savings. This was in a lab. We had the opportunity to try it out in an actual building on campus. This was the building in 2005, our main administration building or university hall building as it is called. We were able to get into a building space, about fairly large space, 2,750 square meters, and it's been working pretty well. We get pretty positive feedback, both from the occupants as well as from the facilities management team. We had another opportunity in 2009 to have this implemented as the base air handling unit in our first retrofitted zero energy building in Singapore at the BCU Academy. And here you can see that zero energy building. This is the naturally ventilated part of the building. So 1/3, 2/3 is air conditioning. So this 2/3 part has this SCTF or single coil twin fan air handling unit design. And in this particular case, we did these measurements. The conventional comparison that we do here, the baseline cooling comes from what it would be if it was a conventional system. And this is the actual cooling that we measured from the BAS system data. So we could see energy savings between 5 and 30%, depending on which unit we were comparing. This was about roughly 2 years, I think about a couple of years after the system had been commissioned and in operation. Let me now talk about some of the other strategies or technologies that we could use, again, thinking in terms of sustainable technologies for the occupant comfort and well-being. Desiccant systems play an important role. There were some presentations at this conference the last couple of days that addressed this. So there is a very good potential. One of the biggest challenges with desiccant system is the need to recuperate the desiccant, and that doesn't always come in easy for buildings, for all buildings. So it's got to be seen in the context of whether we have renewable energy or waste heat in that form to be able to recuperate the desiccant. Heat pipes, another interesting technology that helps us to have good humidity control. And I'll report one study that we had done through one of my students. And a heat pipe basically is for, say, the outdoor air system, the conditioned outdoor air system. Your typical or conventional cooling coil just gets wrapped around by this heat pipe. There is an evaporator section and there is a condenser section. The idea is as the warm, humid air goes through the evaporator section, the liquid refrigerant vaporizes, and then it is moved forward to the condenser or the reheater section, where it passes its heat to an overcooled and better dehumidified airstream. So you got your humidity right, and you also have your temperature sort of corrected in a fairly energy efficient manner. Heat pipes basically transfer the heat from the upstream side to the downstream side of a coil, and in the process of doing so, it also reduces the cooling capacity requirement of this coil. So this is the concept, this is the theory. What did the actual installation show us? So when my students did the measurements in the different parts, well, these points, 1, 2, 3, 4 are the places where these sensors, were the temperature sensors and humidity sensors were placed. And doing some analysis from there, we were able to show about 18% energy savings. And this was for 100% outdoor air requirement. So it was a fairly challenging task, and that's what was done over there. Now I want to talk about this, probably the last couple of technologies. I can see my time is also running out quickly. I will focus on a couple of different strategies on this point and leave you with the flavor of what personalized ventilation system can really do for us. I had a few more slides here on personalized ventilation system, which I'm probably going to be needing to skip in view of the time, because I would like to highlight both the PV system. For me, the PV is personalized ventilation, and the last technology that is an add-on to this PV system. So what exactly is a personalized ventilation system all about? To deliver conditioned outdoor air directly to the occupant breathing zone. This is a concept that is fast catching up in the overall concept of good microenvironmental control. This notion of personalized microenvironment. Can we think in terms of future built environment designs where each person, no matter where he or she is seated, including exactly where you're all seated, where we have been sitting here for the last couple of days, it's not impossible to conceptualize that each seat could be a personalized microenvironment. Easy to imagine or visualize this for those beyond the first row. There's no reason why we can't think in terms of the chair, the rear of the chair being the outlet of personalized air or ventilation air for the person sitting right behind. This has been tried in labs in different format. I don't have the time to go through the literature of that, but the concept essentially is, can we think in terms of a concept of personalized microenvironment? It will certainly enhance ventilation, certainly enhance indoor air quality, enhance thermal comfort. Each person gets his own microenvironment. So I'll just probably talk about one such strategy that we did in a little bit of detail, and then we move forward to the last of the technology I mentioned to you. Here is a desk-mounted personalized ventilation system, office space, desk kind of mounted, integrated with the conventional ceiling supply mixing ventilation system. So here is a photo of the facility, the chamber, the environmental chamber where we did this. So you can imagine, well, this looks not so aesthetically pleasing, our very first version. We work with architects a lot, so the architects told us, well, we can do a better job than what you guys have done here, but as a concept, to show that personalized air can be delivered to a person where he's seated, we went through with this process here, and then this room also had, there you go, the ceiling supply, conventional ventilation, conventional cooling system. When we use personalized air, no ventilation, no outdoor air is provided to the central system there. Okay? All the ventilation comes from the personalized ventilation device here. So in our experimental protocol here, there were some of these parameters that were measured. It is indeed required to be able to substantiate some of these claims that we make. And this was a PhD work, in fact, a couple of PhD work involved in this. Ambient and PV air temperatures, in other words, the temperature coming from the background system for cooling, and the one that's coming from the PV system. Thermal comfort parameters, we measure the breathing temperature in the occupant breathing zone. Concentration levels of various pollutants, important to ensure that the indoor space, the pollutant levels are within reasonable limits. And of course, we use tracer gas measurements to measure the ventilation effectiveness. And a very important part of all such studies that we do when we check and when we kind of evaluate different systems is to be able to include a human response studies. No matter how fantastic a technology we might come up with, if occupants don't like it, that's going to be the end of it. So we include human response studies, subjects being asked to come and participate in the experiments in the environmental chamber. The field questionnaires is absolutely important for us in terms of what we do here. So here is a study here where I'm showing you ventilation effectiveness compared to a mixing ventilation system. Personalized ventilation system gives us tremendous advantage. The number is 1. A value of 1 is what you get from a conventional mixing ventilation system, the kind that we use in ceiling supply systems. With personalized ventilation system, we get about 1.4 or higher, and that's good. When you increase the ventilation effectiveness, that is absolutely beneficial from the point of view of providing that immediate microenvironment. What did people say? They liked it. Here you go, thermal comfort, higher the number, the better it is. There you go, all the blue ones with PV, they liked it. What about indoor air quality? Again, the same story. These are subjects that did not know what they were experiencing in the environmental chamber. Okay? So they just respond to the conditions they experience, and they like the indoor air quality as well. Now, the other big advantage that we see moving forward with personalized ventilation system is the fact that if you can keep the microenvironment comfortable for thermal comfort, indoor air quality, you can actually raise the temperature in the background. And that's going to be tremendous energy savings. These have been reported in journal publications, and you can save energy that way too. You don't have to cool the whole space for a 23 degrees Celsius environment. You can make it slightly warmer. So these are the advantages of personalized ventilation system, and as I said, I'm really running out of time. I'm going to go towards the concluding remarks. I'm going to skip these parts. These are extensions of different forms of personalized ventilation system. I will just mention about this concept of incorporating a personalized ventilation system with a personalized exhaust system. What that means is, from the point of view of airborne infection control, if I'm going to be talking about a healthcare setting, a doctor's consultation room, the doctor is constantly exposed to patients walking in, and he wouldn't know how contagious that person is until he diagnoses the patient. But that immediate process of consultation has its own risk. So if we can incorporate an exhaust in the chair where the patient is seated and provide personalized ventilation for the doctor, this is another PhD study that was successfully completed a couple of years ago. I don't have the time to go into the details, so I'm just going to say here that this combination of exhaust with ventilation is another interesting and useful strategy from airborne infection control mitigation point of view. I'm going to skip this part. Let me come to my last slide, and that's my kind of concluding remarks. I started off by saying that we look at sustainable HVAC technologies. That's my focus of what I'm going to talk to you about. And in the process, what I tried to highlight was why we need to have these energy efficiency and comfort and air quality together, because that is the way to go. We have to talk about micro-environmental control, personalized environmental control for people to be able to create their own microenvironments. And in that process, we will be able to achieve sustainable design in operation at all times. Thank you for your attention, and with that, I'll be happy to take any questions that you may have.